So for these last two examples in 5.2, just differentiating them because they do follow the rules of the stuff that we've learned here in 5.2. They're just a little bit extra, a little bit more going on here to talk about. The idea here, this looks more involved than anything we've looked at currently. And you might be tempted to say, well, look, I can just multiply this out, distribute this, combine a bunch of like terms, and you technically could and create another polynomial. However, what we want to be able to see this as is a pattern, much like I've been describing the quadratic form as an x squared x no x. Well, here x is this whole binomial. This first term is this thing squared. The next term has the binomial. The last term doesn't. So one approach you can use is something called substitution. And you can pick any variable you want other than the one being used in the problem. So I'll actually pick x and say we're going to let x, you put the word let x represent that whole binomial, the z plus 5, because that will take this polynomial and with that substitution or replacement, turn it into 8x squared minus 2x minus 3. Much simpler to work with, something we've seen before. We can start with this now. Now we're not going to forget about this. We'll come back to that. But we can then jump into the problem here. We can do things like, say, the GCF of those terms is a 1, and that 8 is going to make this a bottoms-up approach because this is an x squared x no x with something other than a 1 out front. So 8 times negative 3, start with the a times c, gives us negative 24. And then you get your different pairs that multiply to 24. And you're looking for the pair that multiplies to a negative 24, adds to a negative 2. That'll be a positive 4 and a negative 6. There's our pair. Bring them over here. For right now, we will stick with the variable we're using of x plus 4, x minus 6. We'll take those two and put the a underneath them, divide both by the 8 in this case. We will reduce 4/8 to 1/2 and 6/8, or minus 6/8 to minus 3/4, and both the denominators will come up. So we'll do all of that just like a normal bottoms-up approach. In fact, I'll even put them in parentheses at this point. The only issue is we can't stop there because that is definitely not the set of polynomials that multiply to give us this. For starters, we're not even using the right variable. So it's at this point when you're in that factored form, you want to replace, you want to substitute this z plus 5 back in for those variables. So to do that, you got 2 times z plus 5 plus 1. You're replacing that x with the z plus 5, and same thing over here. 4 times z plus 5 minus 3, and then you do a little bit of distributing, a little combining like terms. Distribute to get 2z plus 10, and that plus 1 is still there. Distribute here to get 4z plus 20, and that minus 3 is still there. Combine the like terms of 2z plus 11, and here you'll have 4z, and that'll give you a plus 17. Now, here's the deal. This is the final factored form. However, this is one of those problems, probably the only problem really that you'll see, where if you go to check this and multiply out those 4 terms to get, or those 4 terms with 4 arcs, you're not going to get this thing, this initial polynomial up here. If you want to check this problem, you would have to basically multiply this out and multiply all of this out to see that they are the same polynomial. Still not a bad idea. If you've got time at the end of a test you're taking, or if we were taking timed quizzes, same thing. Not worth, it's certainly worth doing, but just to point out that this is the problem. You cannot just multiply out and immediately get back to where you started. But this would be our factored form. All right, and for the next one here, this is another one where you can use substitution because what we're going to point out is this is an r to the 4th r squared and then no r's. Notice that GCF is not going to change anything here, right? GCF is 1. And so that's not helping us. We're not going to get rid of those extra powers of r and be left with an r squared, r, no r. But the pattern of r to the 4th, r squared, and no variable at all, if we let, and I'm just going to stick with x again, if we let x represent something, to turn this into an x squared, x, no x, we got to think about what that would have to be. Well, if I want this to be an x squared term, this to be an x term, and then this is a constant, point out this is supposed to be an x term would mean that r squared would have to be what x represents. And if I just write that, if I say x is r squared, think about what the first term would then be. If this is supposed to be an x squared term, if x is r squared and I want x squared, I'll even just write this off to the side, then x squared would be r squared squared, which would absolutely be r to the fourth. So x can represent r squared, x squared can represent r to the fourth, and we can do that substitution and get this to be 6x squared minus 11x plus 3. So that substitution there, we'll come back to in a minute, gets us into that form. We already said GCF is 1, and now we can say there's our pattern, and it's time for the number game. So 6 times 3 is 18, 1 and 18, 2 and 9, and 3 and 6. And the numbers that multiply to 18 but add to negative 11 would be a negative 2 and a negative 9. So we'll go with x minus 2 and x minus 9, and then take the 6, make that the denominator, reduce it to a minus 1/3, and a minus 3/2. So again, just the standard bottoms up approach to get us into this form here. And then once we're there, the factored form, we bring back in that substitution we did. Each of those x's actually represents an r squared. Like that. And then, assuming this can't factor further, that is our final factored answer. And so as I put that in the box, I do want to go ahead and mention this approach, this whole substitution approach absolutely works. You do enough of these and you start to realize that with this specific pattern of r to the fourth, r squared, and no r, you really are just doing the number game as you would, but instead of the, in this case, x's, like it was x's here, it's the variable squared, right? R squareds. That's the only difference in this process, is that these are the variable squared instead of just a variable. But I still recommend utilizing the substitution approach. It's good practice for the other one where it helps too, for anything like this, until you get very comfortable with them.